Okay. So another example for stress strain then. Let's look at the problem. You think you've got this in the booklet, so there it is, example number 3. A tie bar has a cross-section area of that, 250 square millimeters, subjected to a pull of 20 kilonewtons. Calculate the stress in the material and state the units. So first off, I've no need to worry too much about making sure units are consistent, because I've just got a force, that's in kilonewtons, and an area, square millimeters. So when I calculate the stress, I'm going to end up with a stress that is a force over an area, so it's a force per unit area. So I use these units. My final stress will be in kilonewtons per square millimeter. And that's fine. If the question stated, or the problem required, the stress to be in newtons per square meter, because I want to calculate Young's modulus, for example, then I would be thinking about converting that to square meters before I went any further. But at the moment, it's fine as it is. So I've got the area, I've got the force, so straightforward. Okay, stress is force over area. So I know the force, I know the area, I can plug those in and out comes the answer. What about this one? A steel cable extends by 3.7 millimeters under a tensile load from an original length of 12 meters. Calculate the tensile strain. There's the answer. So I'll start you off and you can see if you can just get that answer there. So if you think about what we were doing last week, we were extracting the information we know with those symbols. So extends by. So if we think about the formula that's involved, stress equals x over L, where x is the extension and L is the original length. You've got that formula on your formula sheet. So I'm told the extension, it's 3.7 millimeters under a tensile load from its original length. So the original length is 12 meters. And I want to calculate the strain. So there's the formula for strain. So it's just stress over strain. Problems? Needs to be in the same unit, yeah. So it doesn't matter whether I convert 3.7 millimeters to meters or meters to millimeters. So long as they're consistent, I'm okay. And then I divide one by the other. And remember, because I'm dividing meters by meters, the units disappear so long as they're the same. So it will be unitless, the answer. So I'll just pause while you have a go at that one and just check you get the right answer.
Did you round that?
How about this one? So again, there are the questions A, B and C. Find the stress, the strain and the modulus of elasticity, Young modulus. And there are the answers. I'll just pause this for a little while, let you have a go at it, and then we'll look at it together just to check you're okay with it. Think about what we did for the others, extract the information that's that you've got, check units are consistent. What are you asked to find? What's the relevant formula? Is it in the right form, the formula, in which case you might have to rearrange it if it isn't, and then put the numbers in. So have a go, help each other with it. Always a good idea to draw it. Often helps, especially if you can draw. Yeah. So it's a square section. 5 millimeter sides, 400 millimeters in length. So I can put that information on. That's 5 millimeters. That's 5 millimeters. And that's 400. So I can work out what the area is. If I want the modulus of elasticity, really I need it newtons per square metre. So there's a good case for converting all these lengths to metres so that you get the right units in this final answer here. Not so important for A and B, but for C you need to be in square metres. So convert each of these dimensions to metres, 0.05 metres, for example. Should I even say 0.005? I'm not on very good form today, am I? 0.005. Thank you. Save my bacon again. Or, of course, 5 times 10 to the minus 3. So I'll just quickly run through the others and give you the answers. You can jot down the answers as we go through the book, and then you can check them off. So the next one, these are the tutorial questions now. Very like the examples, so you can take time to have a look at these in turn. That's the answer to number 1. The stress turns out to be 80 meganewtons per square metre, according to me. If you look at number 2, you've got a steel column subjected to a compressive force. Calculate the strain, and it turns out to be 0.19 times 10 to the minus 3, to 2 significant figures. So just jot down the answer so you can check, and then have a go at it. Okay, next one, vertical rod. There are the answers, jot them down. Part A, the stress turns out to be 10.5 meganewtons per square metre, and the diameter of the rod 60 millimetres. Next one, hollow pillar. Calculate the maximum load, turns out to be 25 kilonewtons, and the decrease in length, 1.1 millimetres. So the strain can be the compressive or tensile. Okay, I'll allow you to, oh, there's one more, I think, isn't there? Yeah, number 5. Calculate the decrease in the column's length. I haven't written that down. Or is that one we've already done? Nope, haven't got that one. What is it, Kieran? According to Kieran. Okay, bit of a question mark by that one, so maybe we'll have a look at that one together when you've had a chance to have a go at some. So I'll pause this and I'll leave. So let's have a look at number 5. I've sort of sketched it out and put the information on. So let's have a look at the question. Got a 1 ton mass. So the mass is 1 ton. That's this hollow cylinder here. And we've got an outer and an inner diameter. So I've converted the outer diameter to metres and the inner diameter to metres. The length is 3 metres, written here. And we're given Young's modulus for the material is 124 giganewtons per square metre, or 124 times 10 to the 9 newtons per square metre. So I've converted that to engineering notation and sketched it out. What's going to happen is it's going to compress due to its weight. And we've got to find the decrease in that length. So what we do is we think of a formula. We're after x, the extension. We're after x. So I know a formula that involves x, which is that the stress equals x over the length, where L is the original length. I know L is 3 metres. So all I need is this strain here. So I'll rearrange this formula for x. multiply both sides by L, and more on that next week when we look at rearranging formulae, epsilon times the length. So I need this epsilon, the strain. So I look for another formula that involves the strain. And that is that Young's modulus E is stress over strain. So I rearrange that formula for strain. So I multiply both sides by epsilon to get it up to the top over here. And then I divide by E to get rid of that. So the strain equals the stress over Young's modulus. So that formula is going to help me with this. Because I know Young's modulus. However, I don't know the stress, sigma. So I look for another formula for the stress. And that's that the stress equals the force over area. And it's in the right form because I want to find the stress, so it's in the right form. I don't know the force, but I do know a formula for the force. The force is the weight, and we know that, mass times gravity. I know the mass, it's 1 ton, or 1,000 kilograms. It needs to be in kilograms. So I know the mass, and I know gravity is 9.81, so I can find the force. I don't know the area, but I know it's a cylinder, and it's pi r squared. Hello, Bob. Hang on a sec. For this cylinder, we've got an outer and an inner. So similar in question 4, actually, I've got to find the area of the outer cylinder and the area of the inner cylinder and subtract one from the other, and I have the area of what's left, won't I? So in other words, that's going to be pi radius outer squared minus, pi radius inner squared. The area of the outer cylinder minus the area of the inner circle. If you're thinking mathematically, you could factorize that. R outer squared minus R inner squared. So now I'm there. Lots of formulae. I know the outer and the inner radiuses, so I could plug them into there to find the area. I know the mass, so I could plug that into there to find the force. Divide the force by the area, I've got the stress. Put the stress into this formula, divide it by Young's modulus, I've got the strain. Put the strain into that formula, times it by the length, and I've got the extension. Job done. Okay? So the thought process is going through my original formula and ending up down here to get the answer. So what I'll do is I'll leave that there. You can come up with the answer. I've wiped out what Kieran came up with, that question mark. See what you come up with, and then next week I'll make a point of starting off just by giving the solution to this, and you can see if you got it right. So that's like your homework for this week, to finish that question off. Any immediate questions before I leave it?